Hello guys and welcome to Computing Fundamentals, the second tutorial for today. I hope you are doing well. All good. So today we are going to do an exercise about graph connectivity, and we want to use SageMath to find the degree of a vertex, and we want to find the neighborhood of a vertex, and we want to display the adjacency and the incidency matrix. Then we will do graph connectivity, how we can use SageMath to decide whether a graph is connected or not. The first thing I will start to discuss today, while you are good, and sorry for being late, I was trying to find somebody to fix the makeup. I have been told to do live stream, you have to do makeup, but I cannot afford it. So, all right, so to use SageMath for today with graph connectivity, I wish you managed to see the class about graph connectivity, the live video. If you don't see it, then I advise you to go and see it as soon as possible. I have been told you have an issue with assignment because you have, or you feel you are under pressure because my assignment is due in assignment 1 is due in week 8, and the second assignment is due in week 12. And this is maybe collide because me and John decide to give the assignments a due date at the same weeks. So can I suggest if we move the assignment 1 to week 7 and assignment 2 to week 11? What do you think about that, guys? Please, if you are happy, let me know in the comment down below. In the chatter box, guys. Do you agree, guys, on moving the assignment to week 7? The later to be no problem. What about week 9? Week 9, then you have 10, 11. Oh, if we do it in week 9, you will have no time for assignment 2. So I think you have to think carefully about that. Yes, and I'm going to show you the assignment today, so you don't feel it's really a massive thing to do. It's not. It's just only a revision of graph theory. So how many of you attending, basically? Let me see. Okay, I have 20. Is there anyone from 255? Also, this applies for the 255 guys. Okay, now I know you want to see the lab sheet that I'm going to use, so it should be available by now in the drive. So just give me 1 second, I will put it so you can see it, everybody. So 255, now you can see the lab sheet. I want you to go and have a look to it. Before I start, I don't hear anything from the guys in 255. Is there anyone from 255, guys? Okay, I invited them to see this live tutorial, but maybe they decide not to show up. So I will start doing my own business with this. So today is going to be very interesting, and it's going to be very nice Python thing to do. So I hope you really enjoy what we are going to do today. Can you refresh the page and you can see it? It should be there now. Can you see me? Hello everybody. Can you see me now? Good to see you again, guys. So we will start doing some business, and I have some interesting things to show you today. So the first thing we want to do is, oh yeah, before I forget, the lecture notes are available now in the About section in the class page. Can you all have access to it? But you have to promise me you need to see those videos before you see the class, before you see the class notes, obviously. So the lecture notes of this module are now available in the About section of the class page. Can you see it all, guys? Do you want me to show you where you can find it? So let's say this is the class page of Computing Fundamentals DT249. When you click here, you will see all the notes. These are the student notes. So basically here you can find them. I will add them after I do add the video by 1 week or so, to make sure that you see the video, because the video is covering and describing the content in different format than the class notes. I think we are good to start, everybody. So I will move this up here and I will go back to my SageMath, and the first thing I will do, if you see now the class lab sheet, let me just open the lab sheet for you guys so you can see it, so we can agree what I'm going to do and what you have to do. So for this lab, I want you to be able to use Sage. Okay, there is another issue I have to deal with. Just bear with me a second, just 1 second. Somebody say he cannot see the lab sheet. Can you refresh the page? Martin, just click on the refresh button. You should be able to see it. Do you want me to upload it here? Or you can see the lab sheet, guys. All right, so the first thing I will do now is we want to represent those graphs using Sage, but I'm not going to represent all of them for you. You have to do it by yourself so you can practice representing the graph in Sage. So I will do graph number 1 and graph number 7, and I will do, for example, graph 9. I will leave graph 9 for you because it looks really complicated and you need to spend some time doing it. I'm not going to do that. Okay, so I go back now to Sage and I want to represent this graph, which basically you can see it now in the beside on the right side of my screen. You should be able to see it. So this is the graph that I'm going to represent. So I will do the one representation on simple graph, and another will be undirected graph. So I will choose G1 and G7 as you can see in the lab sheet. So let us start by G1. Now for G1, as you can see from the diagram, G1 is a simple graph, and we have vertex A is connected to B, B is connected to F, F is connected to E, and B is connected to C. Now there is also a vertex called D. And what we call this vertex, guys, based on your understanding of the material we covered in the previous weeks. What we call vertex D, anyone? Can you hear me, guys? Hello? Isolated. It is an isolated vertex. But we will know now how we can basically do such an isolated vertex in Sage. So go back to Sage, and I will create a variable called G2. And this G2 will be a graph. And this graph, I will open now a new list. Now vertex A is going to, I open another list, it's going to B and F. So this is what I have vertex A, the relationship that I have vertex A for. So A is going to F and going to B. And to represent this, I just start with A and put the endpoint for vertex A in the list. Now the second vertex, I start again, which is B, and B is basically going to. B is going to F. Now you need to put those in single quote because these are going to be the name of the vertex, and we have letters instead of numbers. And it's going, B is going to F, and it's going also to E. Is there anything else B is going with? Yes, actually B is going to C. So there is an edge between B and C. Now I finish this and I will start with vertex C. Do I need to represent C? No, because it seems to be C is going nowhere, only to B. But the only edge I have is CB or BC, and I have already covered it by the previous definition. So I don't need to add another set element or another subset to be accurate for vertex C. Now I move to F, and F is going to the vertices A and E. Now finally I have D, and look how I am going to represent an isolated vertex in this graph, and it's going to an empty list. It's going nowhere. So this is the graph I have to represent the graph in G1. I put my mistake here, G2, which should be G1. So A is going to B. Now I want to verify. A is going to F, and we have B going to F and E and C, and F is going basically back to A and to E. By the way, F and A here, it's unnecessarily declaration of this edge. But because we are putting the endpoints here, not the edge set, not the edge subset, we need to define that F is going back to A. Okay, that should be G1 and run. So this is how my graph looked like. You cannot see the here the vertex D. You can see it now from my screen. Here the vertex D. So this is the first thing we want to do. Now the lab sheet is asking you to find a few things about each graph. So if you go back to the lab sheet, it's telling you, I want you to find the degree for the vertex A in each graph, and then you need to find the neighborhood of vertex B in each graph, and you need to display the adjacency and incidency matrices for this graph. So I go back to Sage, and here maybe I should insert a new cell, and I just do, as we learned before, G1 dot degree. I call this method and should be sufficient to put the degree of the vertex, and if you just call it as it is, it will display all the degree for every single vertex in the graph. So the degree of A is 2, which is true, and then I want to insert or to find out the neighborhood of B. So this is neighborhood or the neighbors of the vertex B. Now look how I put every single vertex. Look how every single vertex is basically passed to the method of degree and neighbors with single quotation. So to find the neighbors, you have the degree of B, G1.neighbors, and then you pass the name of the vertex. Yes, I can see you guys. You will have it like in few seconds. Just try to be patient, okay? I can see it. Now you can see the page, so maybe because I'm using Eduroom, so you find this problem. And you can see it. And now, can you see it? Hello. Okay, good. So what I just did before the screen was in a blackish things. So what I did is just only I did print the degree of the vertex A. Okay, I can do that. Yes, I can remove the graph. You want? Guys, you ask so many things today. So this is a graph 7, should be gone now. And you can see now you can see now the isolated vertex D. Yes, I will remove them. Now you should be able to see it without G1 and G7. Obviously you have them already there in your computer. Okay, all good now. So try to print the degree and neighborhood of the vertices A and B as explained. Now the last thing he wants me to do is just to print the adjacency matrix for this graph. So I will do that. Move up to show the whole cell. Okay, relax guys, relax. Okay. Wait, I could copy it and paste it in the chat box, which is the best in your case. So this is the formula for G1, okay? All right, so do you want to take time to represent it or I carry on? I bet you are missing the college and you're missing this cup of coffee. I'm very sure. Poor me, I have to come and you don't. Okay, to carry on. Now I want to print the adjacency matrix, so G1.adjacency matrix, and then I will have another thing to print the adjacency matrix. So we will have incidency matrix now. And I will call it Control Enter to print the result. Yeah, because I had no time to go across the road and buy a decent coffee. That's a pain. Agree. Okay, so now we know how to do the degree, we know how to do the neighbors, we know how to do adjacency matrix, and we know how to do incidency matrix. Now the next thing I want to show you, it's a nice trick, because you see in the lab sheet, I'm asking you to print all of that for 7 or 8 graphs. To waste the time, what we do normally as a programmer, what we do when we have a routine that we want to repeat again and again, we define a function, and every time we want to print those things for a graph, for any object which is a graph, we basically pass that a graph to a function. How you can do that? Things are really simple. You see, Sage is Python based, so we need now to define a normal Python function. And the reason why I'm teaching you this, because you will find it really useful when you are dealing with multiple things at the same time, and it is very good to have your code formatted in a proper way. Okay, so the first thing I will do is to define a function. Now let me go back to my screen and open a new cell. Okay, now I will work in my first function in Sage. This will be to print. I will pass L to it, and the first thing I will do is to print the degree of A, and this should print the variable that I just defined in the signature of the function dot degree of A. Okay. Now, the second thing I will do after that, okay, guys, focus with me how I define this function, okay? I don't want to to be lost. Print the neighbors. If I know how to spell neighbors, I will be fantastic today. R, comma, and this should print L dot neighbors. There's something called copy paste. I should reuse it next time. And this is neighbors of B. And the next statement is going to print the adjacency matrix, and I will print L dot adjacency matrix. The bad thing that inside function you don't have the autofill feature that you enjoy doing or you enjoy using in Sage Cell. After we print the adjacency matrix, I want to print the adjacency I want to print the incidency now. And this should print L dot incidency matrix. Now this function is going to return nothing for me, so return semicolon. Hopefully George is not complaining about my Python skills. Okay. Now I should run this function to be declared. Degree, I think I have a mistake. Wait, degree. Wait. It's not working. That's expected. Okay. Now I have to use copy paste because I don't know what's going on. And cell below. Now I want to print all of these for my graph, so this to print, and I will pass which graph I will have is G1. Oh, I have to run this first. Yeah. That's the issue. You have to click here and run it first before you get it here. So now it's print everything for me. Let me switch off my phone before you start to hear my incoming messages alert. So this is how I define the function. And this is the syntax of the function. I will post it in the chat. Okay, so you can copy it and paste it. I can't copy. Yeah, finally George speak about my Python skills. So I will post it now in the chat. So many strange things happening today. For example, I can't paste. I can't paste, guys, and say so. Can you see the definition in your screen? I add it as a text. What? It's not working. Unfortunately, I can just post 200 words in this thing. So this is how I define a function, guys. So feel free to copy it, or later on I will put the syntax of this function in the classroom page in the comment section. Okay, now I will keep this here in case you need it, and I will insert a cell here above this cell. So I will work with the next graph for the people who wants to know how to create a diagraph. So graph 7, as you can see in the lab sheet, is a directed graph, and we call it diagraph in Sage. How we are going to represent it using SageMath, I will show you now. Just let me quickly just show G2, and then I will switch it off until I finish the definition of it. All right, so I will call this D1, for example, and this is diagraph. And this diagraph, I have vertex A. I need to say it while I represent it, so it's very hard. And vertex A is going all the way to A because this is a loop. Now the second vertex I have is B, and B is going to A, to C, and vertex C is going only to D. So there is one path I need to define, which is to D. And we have vertex D, and this D is going to where is D? D is going to B, and it's going to A, right? So D is going to B and is going to A. That's D. D is going to B and it's going to A. Okay. Now what we have finally, so C is going to D, D is going to B and going to A. That's right. And there is also D going to C. Okay. Now let me go again. A is a loop going to A, B is going to A and C. That's cool. C is going to D, and D is going to A, to B, and to C. That should work, if I am lucky. So this is how the graph look like. It's a diagraph, and this is how it look like in Sage. Maybe I copy this, guys, for you so you can see it. All good, guys, so far? Now, if I want to print all the properties of this graph, all I need to do is to call toPrint and the name of the variable of the graph, which is d1, and just run this function. It should be able to print everything for me. Will print the adjacency and the incidency matrix all at the same time. Now I want to give you like a few minutes. Let's say take 10 minutes and do a graph number. So we go back to the, let me just choose some complicated example so we can do it together. You try first and then I will do it with you. What about you do a graph number 2? I think 2 is cool because it has multi roots and it has also loops, so it is nice thing to represent. So take like 5 to 10 minutes, guys, to do graph number 2. Call it D2. Let me go back. YB is not neighbor. Neighbor of what? B is not neighbor. No, it is ABD. You see, this is the result. You switch back. Sorry, I have a question, guys, about why B is not neighbor. No, it is. B is neighbor of A, so you can see it here down below. I did. Now, who wants to tell me why the degree of the vertex A is basically showing up in this example with 4? Why it is 4? Who can tell me why the degree of vertex A is 4? Okay, so maybe you represent it in different way. Show A, C, and D. Okay. Maybe you have not defined the relationship between vertex A and vertex B. Now, if you go back to the definition of the graph, I have B. I technically say B is connected to A and connected to C. So A is included here. And then I say D is connected to A and it's connected to B. Okay, Mark. So loop complement to degree. Now, you know that there is something called in degree and out degree. When you call the function degree, you are basically asking whether it is in or out. Now, A, there is one path going from, one edge going from B to A and one going from D to A. So this is 1 plus 1. Now the loop is going outbound 1 and inbound 1. So that is basically 4. That's the reason why the degree of A is 4. I think she is right, guys. The neighborhood, I have it wrong in the function. It's the neighborhood of B while we want the if A while we want the neighborhood of B. This is what the lab sheet asking us. Oh, I think I need to drink more coffee. Wait. So, yes, you are right. It's the neighbors of the vertex B, in this case, are A, C, D. That's right. But if you change this in the function to A, you will get the same result I got. And if you go back to the graph, you will find that it is true. The degree, the neighbors are basically A and C and D. Yeah, she's right. That's right. So, sorry for that. I had like a typo here. It should be the degree, the neighbors of B. This is the lab sheet asking me the neighbors of B, not A. Okay, who finished, guys, the graph number 2? Or you need more time to do it? Let me go back to the lab sheet so you can see what I'm talking about. So we want you to represent the graph number 2. Be careful, you need to see the graph while you are doing the representation. Okay guys, so you managed to do the graph number 2 in Sage, so I will try to work with you all together to do it. So the first thing, I will go back to my Sage and create a new cell. And this will be D2, and it is basically a diagraph, right? So I have to represent a diagraph. Now in this scenario, what I have diagraph where we want to build the edge set, where we have A, and A is going to A again, because there is a loop, and it is going, you know what, it should not be diagraph. Wait. No, it is not diagraph. I could use symbol graph to do, because there is no direction in the edges, so there is no need to represent it using the diagraph. Apologies for that. So this should be, guys, G2 graph, and this graph should be basically an edge set where we have A, and A is going to, come on, that's confusing now, A, and then I will go to B, and then I will go to B, and I will go again to B. This is how A is working, and then there is E, and A is going to E. Okay, now I carry on, and the next vertex that I will want to represent is B. So I'll start with B, and B is going to, now I start to mix numbers and text. B, and B is going to what? To E, and D, and it's also going to C. After that I have C, and C is going to C as a loop, and it's going to D, comma D, comma D. Now I'm afraid that the cell is not perfect enough to finish. No, I have only C is going to B, so this is already covered. C is going with multiple edges to D, 1, 2, 3, I have them, and finally I have the graph, the vertex D is going to E. The last thing I want to do is to say multi edges equal hetero, semicolon, and this is should be G2. Oops, I want this to be maximized, so maybe we have more space to see the result. So this is my graph. Now let me just compare them quickly between what I have in the lab sheet and what I want in this. Okay, you want me to copy this and paste it in the chat? The CA? No. By the way, I want you now, after this, after we do this, Martin, I will upload the assignment so we can discuss it today as well. Because I don't think we will have time in the lab to discuss the assignment. So now I have this graph, which is basically multigraph, and I represent it in the same way it was drawn in the diagram. Now take some time, guys, take another time to do, for example, let me choose something easy. Graph 8 sound really good, so I will put now back the lab sheet and you can do graph 8 while I just upload the assignment to the classroom page. I will mute the mic, so don't wonder why the audio is not there. So take 10 minutes, just do graph A. If you have more time, do 9 and do 3. Okay guys, I back again now. The assignment is available on the class page, so feel free to see it and ask me if you have any questions about it. The first thing I want you to do is not Sage. So no Sage code is needed to complete the assignment. So question 1, definition. God, your name in different language. A Word document. Yeah, but don't copy and paste the definition from my slide as it is. You need to define, for example, what we mean by a simple graph, and you need to give a model, an example. I prefer something different from computer networks and airline routes that are presented in the book. Don't use the same images that I have in my slides or in the book, okay? Use something else. You can use, for example, simple graph for Lewis route. Can you hear me now, guys? What's going on? Hello? Anyone? Can you hear me? Okay, good. So, what I was saying about the assignment, before I forget, the mic is in mute. First, you don't need to do Sage for doing the assignment. You need to define those graphs. For example, simple graph, you need to put the mathematical definition, okay? And you need to give example to model, for example, a computer network or an airline route. You could use something else. You could use, for example, the Lewis map, the Lewis route, the train route. You can use different aspects of modeling where you find graph theory is a very appropriate to model. Now, the mathematical definition, don't copy and paste the same mathematical definition that you have in the slides, that you have in the material. Try to define it in your own words and use that mathematical definition as a reference. In question 2, we want to state your understanding of Euler's theorem, and you specify what this theorem, basically the actual mathematical definition of the theorem, and I want you to prove it using the same technique we learned in Fundamental 1. God, don't use audio room to stream. Are you in the college? Declan, if you are in the college, come to my office. It's much better for you. Okay, and then you want to give the proof of Euler's theorem, and finally in question number 3 you are giving a set of directed graph. I want you to determine whether we have an Euler circuit. If there is one exists in the graph, I want you to give me evidence, mathematical evidence that there is an Euler circuit exists in those graph. And then I want you to do, basically, to construct if there is an Euler path. So you want to test first if there is an Euler circuit and an Euler path. Now what you can do about this question specifically, you can solve it in Sage, see whether each graph has an Euler circuit and or Euler graph, and then build your mathematical proof based on Sage. Or you can use the method that we learned in the class, and I'm going to post the Euler circuit and Euler path lecture video this weekend. So you can basically use the theory to prove if there is a circuit or a path exist. Okay, are we good with the assignment, guys? Are we good? And maybe I ask how you find Sage, because the previous year students, they really love Sage. They enjoy doing the graph theory in Sage. And I do enjoy doing the graph theory in Sage. I find it really fantastic, really easy to use. I think the most annoying part is when you want to basically represent something. When you want to represent a complicated graph in Sage, it takes a little bit of time. But after practicing, you will find it really easy to do so. So for question 3, whether you choose to prove it in Sage, and I show you, by the way, a nice feature in Sage that I just discovered yesterday. You remember when you had an issue with saving the Sage file or print it? You don't need, really, you don't need to do so. If you are using your the virtual machine for your with your work laptop, all you need to do is to go to File and download as a Python. Once you download this file as a Python, you can see it really as a Python code. All you need to do is to share with me or with your colleague the Python code. You don't need to worry about basically printing the whole thing. You can basically print, you can download it as different format, but you have to install a plugin. For example, LaTeX, you have to have LaTeX available. For IPython, I'm not too sure what you need to do. For printing, you just do print to preview, and this will print the whole sheet for you. But I know from previous year that you had a problem with this. So an easy way, easy method, just to go to File and download as a Python code. I could show you how, you don't need to see it, but just in case you wonder how this look like, it's basically look like this. I have a Python code. I'm going to open it now, just bear with me a second. And scene 2, quickly add a window, and this is going to be Sublime. Where is my Sublime? Okay, so this is the code, how it's look like if you want to do it in, just to download the SageMath thing. It's really nice, a very nice feature. So you see now I have the Python code. I just download it as a Python, and I can open it in Sublime or in any text editor. It's just only a pure Python code, and it's very easy to submit the assignment. It's very easy to share it with your colleagues and so on. Okay, so we are good about the assignment. We know what we want to do, and finally for today, I have one last thing before you start to do the work yourself. I want to show you is the last thing. I want to show you how you can prove a theory or a theorem in SageMath. So after we finish all of these representation in the lab sheet, guys, there is something I'm asking you to do at the bottom, which is tutorial sheet. Okay, so the task, you want to use Sage to prove the handshaking theorem for graph 1 and 8. As I showed you before, And instead of repeating the code again and again, what you need to do is just to create a function. So now I will create a function. I will show you how you can create a function to prove the handshaking theorem and use that function as an example to do the assignments and to do the rest of the lab, what the lab is asking you to do. Okay, so back to Sage, add a new cell, in Sage, and we want to define a function. Do you have a question, guys? Is the CA still due 29th of October? Is this 29th of October week 7? I think it is. Let me quickly check. Okay, academic calendar. It's week 8. Okay. So do you want it before week 8? Because you need to focus in John's. I will update it now. So instead of 29th, it will be 22nd. Okay. Just stay with me, guys, until I do those housekeeping things. So the assignment is due in 22nd of the 10th. All good with that, guys? For some reason, I thought 29th is the end of week 7, not week 8. Okay, all we need to do is just to change 29th to 28, 29th to 29. Okay, back to our things. So 22nd, I think it's a very easy assignment to do. So I will go back now. I will define the handshaking function that I told you about, and then you will start to use it later on to find out for each graph whether the handshake theorem stands or not. Okay, are you with me, guys, or are you still thinking about the assignment? Okay, so for the handshaking theorem, I will define a function, and this function I will call it, for example, handshake. This is a new Python function. I will create now a variable which is the sum of degree. You see the handshaking theorem that we have the sum of the degree of every vertex in the graph, okay, equals 2m, where m is the number of edges. So I will make the sum of degree, and I will initialize it to 0, and then I do a loop for v, a vertex in the graph, and here we want to check the function. I need to pass the graph here as a variable, so I will make it h dot vertices. This is a function that gives me all the vertices in the graph. So for v, a vertex in the list that returned by the function vertices, that's my function, how it's going to be iterated. At this stage, the sum of degree equals the sum of degree plus, now the name of the graph is h dot degree of, basically I'm going to pass the vertex v, because this is the vertex that we want to calculate the sum for it. I now print the sum of degree just to make sure that I am getting the same the right result. And now I do if statement, if the sum of the degree equal to multiply h dot the number of degree, which is basically can be obtained by calling this method number of edges. Now this is will return, if that's true, 2m equal the sum of the degree of each vertex. Else, okay, else will be return handshaking is not true. Okay. Now that's my function, how it looks like. I compile it, and now I will add a new cell. And the reason why I keep adding a new cell in my case, because I want to keep focus on the cell. I want you to see the cell that I'm working on. So I will add a new cell, but you can basically create as much cells as you need. And I will pass now the handshake function, and I will pass the graph for it, which is a graph number. Let me see if I have G1 and G2 already defined, because I need to be careful about that. Handshake of G1. That's excellent. So I have now the sum of degrees basically 12, and I could just print here the value, which is 2 multiplied by the number of edges. Okay, just to make sure that I am getting the actual result. You can run this again. Yes, so the 2m equals the sum of the degree of each vertex in the graph. You can call it for D1, and you can basically call it for any other function you have created before to do this lab or this tutorial. Now your task is basically now is to do something else, which is supposed to be an interesting one for you to do. Now the task that you are giving today is basically this. I want you to use Sage to prove the handshaking theorem for graph 1 and 8. You can copy and paste the function I just create. And I want you to use Sage to represent a cube graph. And for the graph 7 to 9 in the above, I want you to display neighbor in the in degree and out degree for the vertex D, and neighbor in and neighbor out for vertex D. And finally, and this is like a challenging task, I want you to write a function to print isolated or pendant vertices in any graph, specifically graph 1, 3, and 9. Yes, Maria, the video is going to be posted. It will be posted, and maybe I will edit it. If it's not really cool video, I will edit it and add fancy music to it later on and upload it. But this video specifically, you will find it available on the channel to see after this session. So, anyone, like, I will leave you to do all those tasks, but before I leave, anyone could tell me what we mean by isolated or appendant vertices in any graph? Isolated, we know that this is a vertex which is basically connected to nobody. But what we mean by appendant vertices? Now, be careful. In Sage, you could find something. I will give you one simple hint how you can use this function. Do you remember when we discussed in the lecture video the cute vertex and the cute edge? Now, the fact is, appendant or isolated vertex, they cannot be a cute vertex. Okay? Because deleting an isolated vertex is not going to make the graph disconnected. Also, deleting a appendant vertex is not going to make the graph disconnected. So if you want to write this function, my recommendation for you, look for a method that could basically tell you which vertex is the cute one, and then you display it. Now you have to figure out how you can basically compare or differentiate between what we mean by isolated. You need an attribute to differentiate between isolated vertex and appendant vertex. Think about it. If you want to share the code with me, feel free to do so. As I show you, just go to Sage and basically save it as a Python code, and you can just send me the Python code. I will be able to see your code. Is there any question before I end this session, guys? Any question? Okay. Well guys, thanks for joining me in this tutorial. I wish you enjoyed it and you find it really helpful. I will see you next week in the lab, where we will have a physical lab, and it will be about isomorphism. Before I go, you need to answer this function. You need just to practice. There is no deadline. This is not an assignment. Create a function to check whether a vertex is appendant or isolated. It's just only an exercise. Now, if you face a problem, or if you want to show or share your solution with me, you are welcome. Thank you very much, guys. You have been epic, and see you in the next lab. Thanks. Bye-bye.